Okay, this is the November 2017 question on the photoelectric effect. It says to you, a teacher in a science class explains how different types of spectra are obtained. The teacher uses the simplified diagrams shown below for the explanation. And it says to you, name the type of spectrum of Y. So if we have a look at Y here, we've got a hot gas, and then light is actually coming out of the hot gas and going through a diffraction grating, and then we are going to see a spectrum. So this hot gas is actually emitting light, so this has to be an emission spectrum, okay? And because it's gone through the grating, you will see lines, so it's like a line emission spectrum. So in 11.1.2, what's going to happen here? Here we've got this emitting light, and then we're putting the light into a cold gas. So that cold gas is going to actually absorb some of the energy. So then when the light comes out on the other side here, it's going to be missing some of its energy. So this is going to be a line absorption spectrum because the cold gas sucked all of those energetic photons up. Now it says to you, in an excited atom, electrons can jump from lower energy levels to higher energy levels. They can also drop from higher energy levels to lower energy levels. The diagram below, not drawn to scale, shows some of the transitions for electrons in an excited atom. So it says to you here is increasing energy, so here is high energy and here is low energy. Can you see the scale on the side here? So it says to you, what are these electrons doing here? Can you see this arrow is pointing downwards? Both of these arrows are pointing downwards. So something is going from high energy to low energy. So if you go from high energy to low energy, you can't create or destroy energy. You are going to have to emit the energy somewhere. So it says, do the transitions indicated in the diagram lead to absorption or emission spectra? It has to be emission spectra because that energy's got to go somewhere. Then it says to you, calculate the frequency of the photon produced when an electron in an excited atom makes a transition from E4, here is E4 at the top, down to E2. Okay, so first of all, we must get how much energy is actually emitted. So let's work out what is the energy change. What is the change in energy? It went from 2,044 times 10 to the negative 18 joules. So that was my, oopsie. Well, it doesn't matter. We're going to come out with a positive answer. But it was at that energy level, and it's going to end up at this energy level. So the difference in the energy. Can you see my problem is I'm not going final minus initial. Final minus initial is going to give me a negative answer, which will show me the energy is emitted, pushed outwards. But for now, we're just going to go with this one, and it's going to give us a positive value, but we know it's being emitted because we know what's going on here. So if you put those values into your calculator, you will get a change in energy of 4,09 times 10 to the negative 19 joules. Okay, so that is the change in energy. But did not ask me what is the change in energy. It asked me what is the frequency of the photon. So we know that equation that links energy to frequency is this equation. E equals HF, where H is Planck's constant, which we read off the data sheet. So here's my energy change, 4,09 times 10 to the 19 equals H, which I never put here for lack of space, but it's 6,63 times 10 to the negative 34 times the frequency that we are looking for. So if you put those numbers in your calculator, you will get 6,17 times 10 to the 14, and the unit for frequency is the hertz or the per second. So this will be the answer, 6,17 times 10 to the 14 hertz. Now it says to you, the threshold frequency of a metal is 4,4 times 10 to the 14 hertz. Calculate the kinetic energy of the most energetic electron So that's the one with the maximum velocity. Ejected when the photon produced in question 1.2.2 is incident on the surface of metal Q. So now we want to link energy to kinetic energy, and here we have this equation here. Okay, so if we come here, we're going to write out the equation. We've got the energy equals the work function plus EK max, but we know that the work function, okay, is equal to HF0 plus EK max, where F0 is the threshold frequency. So first thing we have to do is we have to know what is the energy of this photon. Remember, we calculated in the previous question the frequency of the photon, but this value over here was the energy of the photon. Remember, it comes from the transition when the electron jumped from the high level to the low level. So my energy of the photon is 4,09 times 10 to the negative 19 is going to be equal to Planck's constant, 6,63 times 10 to the negative 34, times the threshold frequency, which is in the question here, 4,4 times 10 to the 14, plus my EK max. Okay, so this is now simple algebra. Once you've put these numbers in your calculator and you do some subtraction, you will end up with 1,17 times 10 to the negative 19 joules for your EK max. Okay, so you just need to know that the energy that you put into this equation is the energy from the transition. You take away the energy to actually cause that little photon to jump off the surface of the metal, and that will give you its speed. Now it says to you, another metal R has a threshold frequency of 7,5 times 10 to the 14 hertz. Will the photon produced in question 11.2.2 be able to eject electrons from the surface of metal R? Well, if you want to eject electrons, the frequency of the light must be greater than the threshold frequency. But this frequency that we found previously was 6,17 times 10 to the 14. So is this frequency more or less than the threshold frequency? This frequency is less. Okay, so the frequency is less than the threshold frequency. So no, an electron will not be emitted because the photon will not have enough energy, because the frequency of that photon is less than the threshold frequency, which I've written here in your shorthand, but you can write it in longhand, that the frequency of the photon from 11.2.2 is less than the threshold frequency of metal R, so no photoelectron will be emitted.